The gravitational force. The first force I believe that you would have come in contact with when you fell as a toddler and cracked your head open. So we'll talk about Newton's law of universal gravitation. One of the most exciting laws out there. And then we'll define the weight, which harks back to the video where we had the foam apples and the Newton. So that'll bring that all together. Let's state Newton's universal law of universal gravitation. We put the universal in front of the gravitation because gravitation is universal. It's a law that applies throughout the universe. It's the force, the gravitational force that's governed by this law is the force that holds the Earth in orbit around the Sun. It holds the Moon in orbit around the Earth. It holds us to the Earth, so we don't fly off into space, which would be embarrassing. It holds the Sun in its motion in its orbit around the center of our galaxy. It's responsible for the attraction of neighboring galaxies. We're on a collision course with the Andromeda Galaxy right now. We're going to collide in about 4.5 billion years. So I hope you're prepared by the time that day comes. It's universal. It's throughout our whole universe. And Newton came up with it. For every object in the universe, every object in the universe exerts an attractive gravitational force on every other object in the universe. And you say, well, hang on, Dr. Does that mean that you exert a gravitational force on this pen? And I say, yes, I do. And the pen exerts an equal and opposite gravitational force back on me. You say, well, does that mean that two people that are standing next to each other exert a gravitational force on each other? That there's a gravitational attraction? And I say, yes, there is. Any objects that have mass experience these forces. Turns out the force is very, very small, not even hardly measurable. Very difficult to measure here on the Earth, the force of me acting on this pen, but there nevertheless is a gravitational force between us, gravitational attraction. And that, I mean it, every other object in the universe. It's just so amazing, so amazing. It's universal. For two spherically symmetric objects, and that's what we'll mostly apply this to. Here's a spherically symmetric object M2 and a spherically symmetric object M1. The force is directed along the line joining their centers. So here's the center of object 1, center of object 2, the line along their centers. And its magnitude is given by this equation. All right, that F represents the gravitational force of M1 on M2, the magnitude of that force, which attracts M2 back on M1. But there's an equal and opposite force of M2 on M1, this force here. That's why we're showing, again, thanks to Newton's third law, these equal and opposite forces pointing in opposite directions but the same magnitudes. But the magnitude of both of them, of each of them, is this force F. And so if you work it out for one, then you have it for the other. And the way you find it is by starting off with this, what we call big G, which is called the universal gravitational constant. So this is the universal gravitational constant. Big G, not to be confused with little g that we'll talk about a little in a minute. Well, that we've already talked about in chapter 3, little g being the acceleration of gravity. This is a different constant, not the same thing. Its value applies everywhere in the universe. And its value is 6.67 times 10 to the minus 11. It kind of rhymes, so I encourage you to just commit it to memory right now. 6.67 times 10 to the minus 11. So you start with a 6, you do a point, and a 6, and a 7, and then times 10 to the minus 11. The units, newtons, meters squared per kilogram squared. So 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. That's the universal gravitational constant. And I do expect you to commit that to memory. You use it a lot in a lot of problems and on the test. Likely on the test. So what else is in this equation? Mass M1, measured in kilograms. Bingo. Mass M2, also measured in kilograms. Divided by the distance between them squared. So this is the distance between the two centers, marked here with an R. And so what does this law tell you? As this distance increases, as R increases, the denominator of this fraction increases. But if the denominator increases, then the fraction itself decreases, and the force decreases. What that says is the farther these objects are apart, the less they attract each other gravitationally, which makes perfect sense, I hope, to you. That's Newton's universal law of gravitation, law of universal gravitation. If the objects have no mass, then there's no gravitational force between them. So anything that doesn't have any mass, which is a photon, for example, then there's technically no gravitational force acting between them. Photon is a packet of light and is massless. All right, let's find the approximate force of gravity between a bicycle. Here's its mass. And a child of mass, 25 kilograms. Assuming a separation of 1.2 meters. And you say, well, hang on, they're not spheres. And I say, well, just assume a spherical chicken, like the joke. And so we're just going to plug in these values. G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The two masses, divide by the distance, and don't forget to square the distance. And this is one place where where carrying along the units really can matter. If you happen to write this down and forget the square, but then you check the units, then that'll save your behind. Because here's a meter squared. And that meter squared is going to cancel this meter squared. Had you not squared the meter, then you would have been in deep trouble, and you would have had a meter ending up right here when you're done. And everybody knows that forces are not measured in Newton meters. That's actually torques are measured in that. Let's check the other units. I've got kilograms. Kilograms here times kilograms here. That gives me kilograms squared. But I'm dividing by kilograms squared, so they cancel each other. Just a way to make sure you're doing well. 12 times 25, or 1.2 squared, times 6.67 times 10 minus 11 gives this number here. Is that a big or a small number? Remembering that a Newton is already a small unit. It's about 1/4 of a pound. We're talking about a billion, something like 1/1000th of a pound is that gravitational force between that child and the bicycle. Completely negligible for all purposes on the Earth. Find the force of gravity between the Earth. There's its mass, 6 times 10 to the 24. If you want to impress your friends at a party, then you just trot out the mass of the Earth, about 6 times 10 to the 24 kilograms. And the Moon, a little bit less, but still a pretty big mass, 10 to the 22 kilograms, separated by the distance that they're separated by, which is almost 1 billion meters. 10 to the 9 is 1 billion, and so we're approaching 1 billion meters. Plug the numbers into the equation, and you get a force that's pretty big, right? We're talking about 10 to the 20 newtons. Convert that to pounds, 10 to the 19 pounds or something like that. That's a big, big number. So like I say, gravity is important at long distances for big masses. Let's define the weight. And we did a hint of this when we talked about the foam apple, the little demo video on the foam apples. Define the weight of an object and derive its relationship with the local acceleration of gravity. So first define the weight. And we've actually mentioned this definition already a couple of times in the video, but we've got to put it down and commit it to memory. The weight of an object is the force of gravity on it. It's just as simple as that. The weight is the force of gravity. My weight is defined as the force of gravity pulling me down, acting downward toward the center of the Earth. Well, from Newton's law of universal gravitation, the force of attraction of the Earth on me, I'm going to call that W. Then we replace F with a W, because I'm defining the weight by this, and W represents weight, is G times the mass of the one object, that's the mass of the Earth, ME, times my mass, M, divided by the distance squared. Now that's the distance between the centers of the two objects. So here's the center of the Earth, here's the center of me, maybe my center of mass or something, and that's Newton's law of universal gravitation. That's what Newton's universal law of gravitation. That's what it says about the situation. Now switch gears a little bit. If you're an object above the Earth's surface of mass m, then we already know that Newton's second law says that the force, the net force acting on you, is the mass times the acceleration. If the only force acting on you is your weight, is the force of gravity, then we can replace this net force with your weight. And if you're in free flight, if the only force acting on you is gravity, then you've got your mass here, and we replace the acceleration with the gravitational acceleration. That's little g, 9.8 meters per second squared. So this is the relationship we actually talked about in the video with the foam apples, the demo video. W equals mg. So I've replicated that over here, and this is one that we'll see over and over and over again. What does it say? This is your weight. This is your mass. And this is the local acceleration of gravity. And close to the Earth, that value is 9.8 meters per second squared. But as you move further and further away from the Earth's surface, this little guy here gets less and less. To prove it, we just compare this equation with this equation. So the W's are the same on each side. The right side, on the right side of both of them, we have a mass right there and right there. And so what that says, since the left-hand sides are the same, and the right-hand sides both have an m in them, then whatever's left over on the right-hand side had better equal each other, otherwise we've got a mistake in one of the equations. Well, whatever's left over on in this equation is little g. And so that's this. And whatever's left over on this equation is big G me over r squared. That's that. So what that says is that this local acceleration of gravity, little g, depends on big G, which does not change throughout the universe. And the way that it depends on big G is you have to multiply by the mass of the Earth, or the mass of whatever object is providing the gravity, divided by the distance squared. So as I increase my distance from the Earth, this distance r, from the center of the Earth to me, as I get further and further and further away, this denominator will get larger and larger. And a big denominator means a small fraction, and little g will get smaller and smaller. And so what this equation here says is that the mass, which doesn't change throughout the universe, mass is always the same wherever you are in the universe, and it's measured in kilograms, must be multiplied by the local acceleration of gravity, which does depend on where you are in the universe. If you're near the surface of the Earth, you're going to have to use the mass of the Earth in here. If you're near the surface of Mars, you'll have to use the mass of Mars in here, or Jupiter, or whatever body you're close to. This does change as you move throughout the universe, and therefore your weight, the force of gravity acting on you, will change. Now, I fully acknowledge that you're used to thinking about your mass and your weight as the same thing, but in physics we make a sharp distinction between them. Your mass is something that does not change as you move throughout the universe, but your weight, the force of gravity, does. Okay, the lunar rover and the lunar excursion module have the same masses that they have on the Earth. However, their weights are different on the Moon than on the Earth, for the same reason. When you figure out that local acceleration of gravity, little g, it'll be less on the surface of the Moon than it is on the surface of the Earth. Let's do a little calculation. This is the relationship that we found between big G and little g. Here we had a little r here with the distance of the Earth being here. But let's look at the situation where you're right near the surface of the Earth. So this is little r. Here's where the mass is. It's close to the surface of the Earth. So for all intents and purposes, little r is the same as the radius of the Earth. Let's plug the numbers in. 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, that's big G, times the mass of the Earth, we already talked about that, about 6 times 10 to the 24 kilograms, and then divide by the radius of the Earth. You can look this up in the back of the book or on the internet or wherever. It's about 6.4 times 10 to the 6 meters. It's about 6.4 million meters, or 6,400 kilometers. Plug the numbers in, and lo and behold, what do you get? You get our old friend, 9.8 meters per second squared, the same acceleration of gravity. This is the local acceleration of gravity near the Earth's surface. So if you will, this little calculation here, given the fact that some of you have seen this 9.8 meters per second squared in your high school classes or other, we're familiar, it's easier to do an experiment. You just drop a rock and see how long it takes to fall. We did a lot of examples like that in chapters 2 and 3. So we're very, very familiar with this local acceleration of gravity. But this exercise verifies Newton's law of universal gravitation in the special case of motion near the Earth's surface. All right, complete the following statement. Near the surface of the Earth, the weight of an object is the same as the mass of the object. True or false? False. Weight measured in newtons. Mass is measured in kilograms. They can't possibly be the same. It's like trying to compare apples to oranges. You have to compare two things with the same units. And they're never the same, these two guys are. The weight of an object is the gravitational force by the Earth on the object. Well, that's true. It's a force that the Earth exerts on the object at that location. It has the same value regardless of the altitude above the surface of the Earth. The weight will get less and less. Remember, the weight is m times g. And as you get further and further from the surface of the Earth, g will decrease. It'll start at 9.8 meters per second squared when you're close to the surface of the Earth. It'll get to 9, it'll get to 8, 7, 6. As you get further and further away, that g will get less. And the mass doesn't change, so the weight has to get less. So that's false. Has the same value, the weight of the object has the same value regardless of the mass of the object. It's also false. Weight depends on the mass and the local acceleration of gravity. So I think we've beat that one to death. A rock is thrown straight up from the Earth's surface. Which one of the following statements concerning the net force acting on the rock at the top of its path is true? All right, we've got a rock starting here, it goes up, comes back down again. And we're concerned about what happens when it's at the top of its trajectory. Let's first say what we know about this. When it's at the top of its trajectory, what can you say about its velocity? Well, up here, you say, well, the velocity is going to be 0, right? It's not moving. At that instant in time, moving up just before it reaches the top, not moving at all. When it reaches the top, then it starts moving down. So the velocity is 0 at the top. What can we say about the acceleration? We talked about this over and over in chapters 2 and 3. What's the acceleration of that rock at the top? Is it 0? No. The acceleration is down. Were it not so, that rock could go up to the top and stay there forever. But we know that gravity is continuing to pull it down, so its acceleration can't possibly be 0. So that's what we know from chapters 2 and 3. But what do we know about the situation from chapter 4 that we're dealing with now? Well, this is an object. It has some mass. Is there a force of gravity acting on that object? And the answer is yes. It's called its weight. You say, well, wait a minute, though. You know, if I jump up, when I get to the top of my trajectory, I feel really weightless. We're going to make a definition of weightless in just a minute. But weightless basically means that the only force acting on you is gravity. It's kind of weightless seems kind of a misnomer if you have weight and you're weightless, but weightless means that the only force acting on you is gravity. So it does indeed have a weight. So let's see if we can answer the question. It's instantaneously equal to 0 newtons. So we're asking about the net force acting on the rock at the top of its path. It's instantaneously equal to 0 newtons. That's false. And how do you know that's false? Because if the net force were 0 and the velocity were 0, then Newton's first law would demand that that object stay there forever. So it can't possibly be true. The net force is greater than the weight of the rock. Well, there's only one force acting on it when it's up here. It's the weight of the rock. So this is not true. It's less than the weight of the rock, but greater than 0 newtons. That's also false for the same reason. Its direction changes from up to down. Well, what's the direction of the weight of an object? As the object is moving upward, here's its velocity. It's moving upward. What's the direction of the weight? The weight is always pulling it down. So that's the velocity. It's going up. The weight is pulling it down. And how do you know that? Well, the weight is acting opposite to the velocity and slowing it down. And on its way down, the weight is pulling it down, and the velocity is also down. So on its way down, the force of gravity is increasing the velocity. They're both parallel to each other. So the weight of the object, does it change from up to down? Well, no, it doesn't, because it's always down. The velocity changes from up to down, but not the weight. That's false. And then finally, it's equal to the weight of the rock. That's true. The force of gravity is always equal to the weight of the rock and always points down. It's like G. G, the acceleration of gravity, always points down. The weight of the rock, which is equal to m times G, always points down. Which one of the following statements concerning G, the universal gravitational constant, and little g, the magnitude of the acceleration due to gravity is true. The values of g and little g and big G depend on location. That's not true. G depends on location, but not, little g depends on location, but big G does not. So that's false. The values of g, both g's, do not depend on location. That's not true, because little g does depend on location. The value of g is the same everywhere in the universe. The value, that's not false, that's not true. Let's just find the right one. The value of big G is the same everywhere in the universe, but the value of little g is not. That's true. Okay. Cell phone is sitting on a desk. Which one of the following is the reaction force of the cell phone to the cell phone's weight? Here's a cell phone. It's sitting on a desk. The Earth exerts a gravitational force on that cell phone that pulls it down. It's called the weight. This is the weight, which is equal to the Earth's gravity pulling down on the cell phone. The gravitational force of the Earth on the cell phone. Pulls it down. All right, so which of these statements is true? Well, we're trying to figure out what the reaction force is to the cell phone's weight. And this reaction force deals with Newton's third law, which says, and let's say that this is, Earth is A, and the cell phone is B. If object A, the Earth, exerts a force of a particular type on object B, what's the type of force in this particular case? It's a gravitational force. So the Earth is exerting a gravitational force on the cell phone that pulls it down. Then object B, the cell phone, exerts a force of equal magnitude and opposite direction on object A of the same type of force. What type of force is this? Gravitational. In the opposite direction. So that says that the cell phone exerts a gravitational force up on the Earth. So remember, cell phone is B, and Earth is A, and the type of force is a gravitational force. We've got normal forces going on here too, and we'll talk more about the normal force in just a second. That's the force at the table holding up the cell phone, but Newton's third law doesn't care about that. It wants to stick with the same type of force. And so Newton's third law says that the cell phone pulls up on the Earth. So that's this force of the cell phone pulling up on the Earth, the gravitational force on the Earth. So what's the reaction force to the cell phone's weight? The gravitational force of the cell phone on the Earth, and there it is. That's the one we want. The normal force, we'll talk more about all the rest of these are normal forces, but it has to be the same kind of force for the reaction force which pertains to Newton's third law. So we'll always use this word reaction force to denote when we're talking about Newton's third law. Ryan walked to a cliff, dropped a stone, neglecting any effects due to the air as it falls vertically. which one of the following is the reaction force to the Earth's gravity on the stone? This is an almost identical problem. Here's the stone. Here's the Earth's gravitational force acting on the stone, pulls it down. That's its weight, right? And it's not going to be a normal force. It has to be the same kind of force, right? Gravitational force of the stone acting on the Earth. So it's pretty much the same problem. I probably shouldn't have bothered that one. And you might be thinking, well, the answer sounds pretty good. As the stone's falling, it's not exerting any force on anybody. It's not pulling the Earth around. And you'd be wrong. The stone, while it's falling, is exerting a gravitational force up on the Earth, and the Earth is falling toward it as well, but it's just not moving very much because it's so massive. Isn't that neat?